Okay, so let's begin lecture 13, week 6, and this is the second lecture on neutron transport. I'll continue from where we finished in lecture 12. Okay, so we had started the one-speed uh, neutron transport equation, where uh, we had integrated over the energy to reduce the number of independent variables from 3 to 2. Now remember, the assumption over here was that collisions are taking place, but there's no energy loss. We also assumed azimuthal symmetry, and so many assumptions were made. And integrating all the terms over the azimuthal angle, we retain the orthogonal angle theta, and mu is cosine of theta. So this is the scattering, scattering in term, and this is the number of fissions taking place, the angular flux multiplied by the fission macroscopic cross section multiplied by the number of neutrons coming out in fission multiplied by the fission spectrum, i.e. the contribution from E prime to E, our phase space of interest. So here we've got an integration over angle, we've got an integration over energy, and then we have the contribution to our phase space of interest. So this simplifies the fission term to a simple integral over here. Now notice that chi of E has disappeared, as it is understood that neutrons emerging from fission will fall in this energy group because there's no other energy group. And finally, we integrate the source over all energies, and we get the energy averaged angular source. So with the above, let's collect all the items and we write a 1D transport equation in plane geometry. So in plane geometry, you can see we've got a d by dx over here. This is the loss term or the outscattering term. So you can also view this as an integral, just like this. But these are for neutrons going out. These are for neutrons coming in, and these are for fission neutrons being produced, and this is for the source. So now we define a quantity C as the mean number of secondary neutrons emerging from a collision by any process. Now, if there is no fission and no end-to-end, then all these terms go to 0, and you can see that C just becomes a scattering probability, sigma S over sigma T. So when this is divided by that, it becomes a probability. So now in this case, C is 1. If you have fission, then C can become nu bar. If you've got multiplication, C can become 2. So when C is less than or equal to 1, we call it a non-multiplying medium, the case for a non-multiplying medium. And when C is greater than 1, then of course that's for a multiplication situation. So with this definition, we can write over here, and notice that here we've got x, the physical distance. Here we've got the optical thickness. Optical distance means that the physical distance expressed in terms of the number of mean free paths. Now, because sigma t has units of 1 over centimeter, so lambda, the mean free path, has units of centimeter. So this is centimeter, this is centimeter. So it becomes a dimensionless quantity. So per centimeter times centimeter, so the unit of distance is measured in terms of the mean free path. So 10 mean free paths is good enough to solve a problem, usually. Now, let's see what insight can we gain from the dependence of this flux. So for the case of a source-free infinite medium case, the easiest case, analytical solutions can be obtained, they have been obtained by assuming separability. Separability in space, separability in angle. And if you assume an e to the minus z over mu for the z term, see both of them are connected over here. So this should come out to be a scaling factor. So you're supposed to assume separability. So you've got eigenfunctions over here, and for requiring that the integral, this thing is normalized, so you can put this value in here and you get this function on the left, and this you get on the right. Now when you integrate this, when you integrate this from -1 to +1, you get this right-hand side over here, which can be expressed in terms of the inverse of the hyperbolic tan by this equivalence over here. So in order to find the relaxation length, which is an order of nu naught, you have to solve this transcendental equation. Now, what I've done is I've got a MATLAB program which calculates, which computes nu naught for c less than 1. Less than 1 will give you real numbers for nu naught. So these are the numbers I get, that for c going from 0 to 1. Now, the case of c equal to 0 means that there's no scattering going on. So when there's no scattering going on, that means it's a pure absorber. And when there's full scattering going on, that means there's no absorption. So this is a pure scatterer, this is a pure absorber, and you can see that the values nu naught are fairly constant over here, then they begin to rise over here. But the point is that they're all real numbers. Now when they're all real numbers, then it becomes easy for us to understand that the flux falls off as e to the plus or minus x over nu naught. Nu naught will have two values. So, so this is the space dependence and this is the angular dependence. Now, if c is near 1, then you can see that when you express 1 over nu square over here, then when c is near 1, then this converges fairly rapidly, and you can say that it's only the first term that contributes significantly. So nu naught square is the square root of 3 times 1 minus c. Now remember, c is sigma s over sigma t for our case, for this case, for a non-multiplying case. So if you write this as sigma s over sigma t, so it becomes sigma t minus sigma s, so that's sigma a, so that becomes sigma a over sigma t, right? So that's what the 1 minus c is. Now, if you remember from the diffusion length in L, which we got from the diffusion theory, the scaling is by about that much. So 1 over 3, 1 over square root of 3 sigma t times sigma a. Now, if you take the diffusion coefficient, then the diffusion coefficient is 1 over 3 sigma transport. And sigma transport is sigma t minus sigma s mu naught. So for a weak absorber, you can say that it is sigma t is about sigma a, and so it becomes sigma a square over here. So that becomes the diffusion length over here. So if you put sigma a is 1 minus c, so it becomes this, which looks like the relaxation length from transport theory for the infinite medium case. Now, what I just showed you was a partial differential equation. It was first order, and as I mentioned in the previous lecture, it is a linear equation. The linearity is so important because you can use the superposition principle, where if you have a number of sources, S1, S2, S3, S4, then you can solve the equation separately for each one of those sources. You can add the solutions for each one of those sources, and that will be the correct solution in the presence of all the sources. So that's what linearity in this context means. And the consequence of this is that you can use Green's function, which is a response function, the response at a detector position due to a source at a source position. Okay, so now what we're trying to do is we're trying to get an integral equation. There are so many ways. And one of the ways is the method of characteristics, which I'll just show you. The other is an intuitive way where imagine that you've got a phase space of interest P. And as I've so many times said in this lecture, even when we were doing Fermi slowing down equation, so I said that we have a collision density, and let's call the collision density chi of P. So chi of P is where we are interested. Chi of P prime is where is all the other phase spaces. So the contribution in P is coming one from the direct source, which let's call S of P, plus the indirect, meaning that let's look at the collision density at P prime other than P, and then its contribution to P would be when this is multiplied by a scattering kernel K, which brings it from P prime to P. So if you take this product and you integrate them over all other P primes, then you get the total contribution to chi P from the indirect scatterings. Now, as I said, that this form is obtained by carrying out an integration of the PDE of the transport equation. Now remember, the transport equation that you saw was an integral differential equation. So it's already got one integral on the right hand side. So if you were to try to integrate it, so then you would take an integrating factor on the left hand side. So then you'd see two integrals on the right hand side. Okay, so let's see how that progresses. Now this was an intuitive expression. So I'll just talk a little bit more about this very soon. For the time being, let's take the operator form L hat operating on phi r omega et, which had four terms over here, one time and three space. And if I write that as a total derivative in terms of the distance traveled s, then I can convert the PDE into an ODE. And the characteristics of this are where t is equal to some starting position, some starting time, and some starting position r naught. So some starting time t naught plus the distance traveled s divided by the speed of the neutron. So then we can write the transport equation as an ordinary differential equation, first order. Now this would give you the integrating factor e to the sigma t times s, and we would then be able to write a compact term on the left hand side. For the right hand side, we'd have to take the integrating factor over there, put this in one, and then integrate both sides. When you do that using the standard methods, then you get this for the flux. And as I said that you've got one integral sitting here and one sitting here. So that's why you see two integrals. One was already there and one has come about by integrating this ODE. So Q is defined over here as the scattering down or the in-scattering plus the source. And this is the contribution that it makes to the phase space of interest that we have. Now the integral equation, you can see that it has a very distinct physical sense that usually when you think of a Volterra equation or a Fredholm equation, you say, how am I going to solve it if the unknown is present in the left-hand side and on the right-hand side? So the standard procedure is to take a guess, phi naught, and put it on the right-hand side over here in Q, because Q's got phi. So put it as a guess over here and get phi 1 on the left-hand side. Then put phi 1 as a guess and get phi 2, then put phi 2 as a guess and get phi 3, and successively go on and on until you get the nth value for phi. And this is what Neumann recognized, that these actually represent the contributions coming from zero collision or from a finite number of collisions. So if you express the solution of the integral equation as a summation of phi n, where n goes from 0 to a very big number, then you can see that the uncollided flux, which means that how many of the source neutrons are coming directly onto the detector. So we call that the uncollided flux. Now the uncollided flux has its own significance. It's very important. And this is the flux uh, that comes straight from your source or reactor or whatever you've got without undergoing any collisions. And then you've got phi 1, phi 2, phi 3, those who have had one collision, two collisions, three collisions, and phi n, those which have had n collisions. So this integral equation that you see over here is actually uh, possible to solve by carrying out an analog simulation. Analog simulation means to simulate events as they actually take place in nature, unbiased. But sometimes, after this lecture, we're going to start Monte Carlo simulation. For that, we're going to study the Monte Carlo method. Monte Carlo methods are based on, the Monte Carlo method is based on probability and statistics. So you'll see that when you want to get good results, then you have to have a small uncertainty. The uncertainty is called the standard deviation. So you want to be as certain as possible and you want to be as accurate as possible. So in other words, accuracy and precision are the two requirements of a Monte Carlo result. So this I was talking about analog simulation. Now sometimes it is in your favor to do non-analog simulation to artificially bias the problem in such a way that that you improve the contribution of things that are important, and you do not give importance to events that are unimportant. So it's like importance biasing. You can call it importance biasing. And when I mentioned to you earlier on in this course the adjoint flux, so you can see that this is where the adjoint flux or the importance function begins to become relevant to obtaining a good answer. Now I told you that the indirect contribution comes from all other phase spaces P prime, which undergo collisions. And when you multiply the collision density in P prime by a scattering kernel, then you look at the contribution into the phase space that you're interested in, which is R omega ET. And so K is a product of a collision operator C and a transport operator T. So if you look over here, K phi is C multiplied by T multiplied by phi. So the first thing that's happening to a flux, a packet of neutrons is that it is being transported at uh, some energy E prime along some unit vector omega hat prime, and they're being transported from their present position R prime to some future position R after delta t time. Now, once they've come to the new position R prime, then they've got energy E prime, and they were traveling in a unit vector direction omega hat prime. So now they're going to undergo a collision. And so in a collision, you've got pre and post collision parameters. Now what happens in a collision? A neutron hits a target nucleus. It transfers some energy to the target nucleus. As a result, it changes its direction. So through the conservation of momentum, energy through the conservation of energy, energy has to be conserved. Through the conservation of momentum, momentum has to be conserved, horizontal and vertical. So the conservation of momentum and conservation of energy takes us to the point where we see that the angles have to change. And so the post-collision parameters become the ones of interest to us, which are R, and so this should have been R because it's now at R. So now the contribution is to the collision density at R, E, omega. So that's what we were interested in. So that was the integral equation. And now let's see again some computational um, uh, ways by which we can make things useful. So one of the ways, as we did for diffusion, is to use a multi-group form for the integral transport equation. Now, how you do that, and there are many codes. For example, the Morse code, the multi-group Oak Ridge stochastic experiment. So this was developed by the Oak Ridge National Labs, and this code is a multi-group code. And I remember in my PhD when I got a listing of it and I used it. So I found it to be a very logical, straight kind of a thing, which you understand things very easily. You divide the entire energy spectrum into discrete number of groups, and you solve the matrices, and you solve for the vector of the group fluxes in the domains of interest. So this is the collision density equation for group G. And again, this is our phase space of interest. So chi of G has a direct contribution from the source, SG, same energy group, plus the indirect contribution of neutrons which had a collision density in some uh, other energy group where the energy was G prime. And so what you can see, of course, this should have been omega prime, because they're being multiplied by scattering, which is taking them from G prime to G. Our energy of interest is G, and which are taking them from, and this scattering process is taking them from omega prime to omega. So our phase space of interest is R omega T in the discretized energy group G. So here is a very neat, compact collision density equation in multi-group form. And in multi-group form, the good thing is that you can see C and T explicitly. So C looks like the summation over all energy groups, D omega prime times sigma S transfer scattering cross section divided by total microscopic cross section at the initial energy. The transport operator is the probability of not having a collision while traveling this distance, and then of having a collision uh, at r in dr. So, so not having a collision, then having a collision. So that is what takes the transport from r prime into r. And when you look at all the possibilities from where this can happen, then you've got to integrate it from 0 to infinity over r. So when capital R is 0, then put 0 over here. So it's small r to r. When capital R is infinity, so it's a contribution from far away to r. So the collision density is tallied, and the simulation continues until a history ends. Now, what is a history? A history is that from beginning of life to end of life. So what is the beginning of life of a neutron? It is when it is emitted as a source neutron, when it begins its life. What is the end of life of a neutron? It is when it either escapes from the system or it gets captured, it gets absorbed, radiative capture, simple absorption, disappears. So that is the end of life of a neutron. Now, between its birth and its death, it undergoes many events possibly. And those events are collisions, scatterings, elastic, inelastic scattering, fission, absorption, N2N, NN prime, N alpha, NP, whatever reaction, N gamma that might happen. So when you simulate all those events and then you do it for one history, you do it for a batch of several histories, you get the average tallies that you're trying to get. For example, here we're scoring for the collision density. Collision density is the number of collisions in an area of interest, in a phase space of interest. What is the collision density? It is the macroscopic total cross section multiplied by the flux. So it's the total number of interactions per cubic centimeter per second multiplied by the volume. So that becomes the interaction rate, and that's what we call the collision density. Okay, so now let's look at the exact solutions of the transport equation. There are so many. There's the Fourier transform you can use, there's the Mill problem, there's the Wienerhoff technique, and there are benchmarks, a number of benchmarks made by Ganapol. So you can go through Bell and Gladstone to see the so many exact solutions that have been obtained for infinite, semi-infinite, in plane, in spherical geometry, with a point isotropic source, with a planar source, and Chandrasekhar's radiative transfer analysis. Because remember that this transport equation was being studied in the 60s and early 70s as the radiative transfer equation for stellar atmospheres. So so most of the exact solutions you'll find a very good place, very good collection is Bell and Gladstone. And if you can look at the work by Ganapol, and Ganapol has a number of very elegant mathematical, compact, exact solutions for several cases of interest also. And for example, he has looked at monoenergetic transport in an infinite medium using the Fourier transform. Then he has looked at monoenergetic transport in a semi-infinite medium using the Laplace transform. Then he has looked at monoenergetic transport in a 1D slab, the FN solution. So, and monoenergetic in a 1D cylinder. Now, these are all fascinating things because when you have a huge code such as MCNP, when you're a student, when you're starting your PhD, or when you're doing your MS thesis, when you're running something like MCNP, or when you are, you come across a huge code and huge problems, and you have absolutely no idea what the answer should be. So this is the thing that you should be doing. You should look at benchmarks. So now this is when I was doing my PhD, so this came to my mind, that how would I know if I'm doing the right thing or not? So I started looking for benchmarks. And now lots and lots of benchmarks are available. So my advice to you is that whenever you do anything big in nuclear design, then you may get lost in a lot of numbers. So before you embark on something, it is worth investing a few weeks even. I wouldn't mind a few months. So I think that there's absolutely no harm if you spend 2 months on looking at benchmarks and take your code and compare the answers from your code, because when you take a big code, you have to learn how to set the input also. Every code has its own nuances, and every benchmark has its own limitations. So you've got to match the code on one side and the benchmarks on the other side. But that's how you get confidence, and that's how you develop an understanding into what you're doing. So even a multi-group slab transport Ganapol has done using the Green's function method. 2D semi-infinite medium problem, he has done the searchlight problem, multi-group transport in a 3D infinite medium using the point kernel method. So some very powerful mathematics. The same is true for publications by Mike Williams. I think these are the people who took mathematics to the edge and showed many of us that you don't actually need to have very powerful computation. You can do a lot of useful stuff if your mathematics is really high level. So now this is what I showed you for an infinite medium, source free. And Ganapol has for the monoenergetic transport solution in a semi-infinite medium. Now in a semi-infinite medium, he has given a solution for a beam source, a torch, and an isotropic source. Isotropic source is a candle, and a beam source is a torch. So if your source looks like a torch of neutrons, then this is the solution. Now the H functions are Chandrasekhar's H functions. So this is the solution where phi, no, phi 0 minus 1 over S, the Laplace transform uh, gives you this solution over here. So now Chandrasekhar and Ganapol and a number of outstanding scientists in this field have used this analysis to calculate what is called the albedo problem. Albedo problem means that if you shine radiation on a surface, let's say I shine 100 watts and 30 watts comes back to me, so I would say the albedo is 0.3. So albedo problem is the reflectivity of a surface. So this was addressed in 1960 by Chandrasekhar, and later exact solutions have been obtained by Ganapol in 2009. So you can see that there's a gap of 49 years. So because these are all fascinating areas, and you can, I mean, if your maths is good, you can really, really get outstanding, compact, elegant expressions. So Chandrasekhar showed, and as did Ganapol, that for emerging radiation, which means mu less than 0, now mu goes from -1 to +1. Mu -1 cosine theta is -1 when theta is pi. Pi is 180 degrees. So when radiation comes back to you, the mu is -1. So between -1 and 0, 0 is the case of 90 degrees. And so -1 to 0 is 190 to 180 degrees, in other words, backscattering, and 0 to +1 is forward scattering. So 0 degrees to 90 degrees. Okay, so for emerging radiation, both Chandrasekhar and Ganapol showed that the solution looks like this. So there's a neat exponential over here, decaying exponential, times phi x over here. Now this is an integral equation. How do you solve it? So it's not straightforward. You can do it by Chandrasekhar's H function. You can do it by successive approximations. So at surface x equal to 0, if you put x equal to 0 over here, so you get the contributions to the surface, the backscattered contribution uh, with e to the minus x prime over mu, because x goes to 0, times phi x prime over here. So the exact solution has been obtained for an isotropic medium with a point isotropic source at the surface separating the half space from the vacuum in terms of Chandrasekhar's H functions. So it's phi 0 minus mu is 1 minus square root of 1 minus c h of mu. Now, if you see, if you've got a pure scattering medium, put c equal to 1, so this whole side goes away. So then the emerging is 100%. So if you plot angle versus the emergent uh, flux as a function of the parameter c, which is the scattering probability, then down here what you've got are low values of c, which means you've got an absorber. So an absorber absorbs a lot and doesn't send a lot back. So as the absorber becomes less intense and the scatterer becomes more prominent, then you've got more things coming backwards, so more scattering. So this is the albedo for monoenergetic neutrons. And if you see that this is how the albedo of the Earth was calculated to be about 0.3. So the Earth albedo was calculated to be 0.3 for the various values of C that were assumed. Now let's come to an exact solution for an infinite medium with a plane isotropic source. Now this has been obtained by Case's method and by the Fourier transform method, which is in Bell and Glasgow. So what they do over here is that they place the source at x naught, and to the left and right of it, they solve and they have a discontinuity at the source position. So you can see that again we get an elegant compact expression in terms of exponentials in x. So there's a relaxation length and the angular flux is separate over here. So on the right side, you've got this expression, and generally you've got this expression. This is the principal value. So this is complex integration, and so you go about the singularity. And so finally you get the flux as a function of x. So phi of x is this expression over here. So this is an exact solution for a semi-infinite medium with a planar source. Okay, so plane isotropic source. Now, angular fluxes are shown over here for various cases of C. Now, as I said, that mu going from 0 to +1 is the case of forward scattering. And from -1 to 0 is the case of backward scattering. So these lower graphs, which you see over here, are the backward scattering. And this dot and this solid curve is the forward scattering case. So you can see that for C equal to 0.2, the angular flux is more when you are at smaller mean free paths. So as the mean free paths go up, the angular flux comes down. Now, the way of plotting this would probably have been a 3D picture. But what I've done in the MATLAB programs is that I plotted this for fixed values of mu. So you can see that backward scattering is less for this particular case where it's a predominant absorber. It's mainly an absorber in an infinite medium. Now, as you vary the value of C, so what you see is that there's an uplift in the angular flux. So you notice over here that the values were all below 10 to the -3, here going down to 10 to the -7. And here there's a slightly higher value. So there's a movement upwards. So there's more scattering. And again, more scattering over here. So these are the various exact solutions. So the flux given can be expressed as an asymptotic and a transient part. And the asymptotic part represents the collision equilibrium component. And this is shown in figure 4.6 for a high scattering medium. So let's look at figure 4.6. So you can see over here that there is the asymptotic flux is reached quickly if there is more and more scattering. And a weak absorber, of course, would never reach the asymptotic flux. Okay, so I think I'll stop over here. And in the next lecture, we'll do finite sphere with a point isotropic source. So we look at the exact solution in spherical geometry. And then we will look at some other solutions. Then we'll come to numerical solutions, because numerical solutions are of great practical importance. When you're solving for nuclear systems, you're trying to obtain the flux. Your objective is to obtain the flux in a nuclear system. So you want to have good estimates of the angular flux. Angular flux determines, for example, shielding consequences. Then is the flux more backward? Is it forward? So you need to have a good understanding of angular flux. So transport theory is very good, I'd summarize, but it's not easy to obtain exact solutions. Now, in the absence of exact solutions, what we do is that we go to numerical solutions. And it's a very, very popular and successful route to solving for the neutron flux, the photon flux in any nuclear system.